Recording in progress. Well, that made me quiet. Okay, so we're going to allow people to get into the webinar. We'll get started in a little bit here. It is, oh, my phone says 12:59, so we probably will go till a minute or so after the hour to allow people to get in, get settled, and pet their cat for one last time.
What's the puppy's name?
Or is that a dog?
Oh
my gosh.
Dog. Yeah.
That
my
dog
dog's name is Tuna.
Hi, Tuna. That dog is, I had to bring mine in here. They're like, they could be brother and sister. Or whether yours is a girl or a boy, I can't tell by Tuna.
Yeah. Yeah, she's a lady.
Ah. So is mine, a lady who will not know her name unless there's a treat involved.
Yeah, I am doing this to avoid any barking that may interrupt. So.
Well, that happens.
alternative.
I have closed the doors on my office, but that doesn't mean she's not going to come and bang on them at some point. Oh, did I tell my mom not to call? That's the other thing. Welcome, who's ever being added in. Ooh, 65 people. That's great. Thank you for joining us. We're going to give this another minute or two to allow a few more people to be added in, and then we'll get started. Oh, I suppose I'm showing up on screen as well. Uh-oh, the Q&A has started already. Let's see what that says. Oh, someone asked if we could turn on transcripts / closed captioning and enable them, please. Is that something we can do, Kelly?
I am working on it.
Great. We're going to try and get that set up. I don't know what's possible. The whole setting up of websites is a mystery to me. And it's going to remain that way, to be honest. We have people like Kelly to help out. Okay, I wonder where I can put Q&A. Looks like over here.
So Jennifer, I'll be watching the Q&A. Do you want me to give you any time warnings for your presentation?
Sure. You can do that. I think I'm gonna, I have 24 slides. Some of them, they're not even a minute long. So I feel like it'll be pretty good. Unless you know me, I start to tell a story. So how are we doing? What time we got? Oh, it's 1:02. We're going to go ahead and get started. Thank you for joining us this afternoon. And you can see me look over to the side because, you know, we all look at ourselves. But anyway, I'm a member of NAMA, which is the North American Hazardous Materials Management Association. And we took on hosting these webinars from EPA. And I'm hoping that you enjoy the series. I feel like after looking at 2 webinars, I want to add another one. There's so much to learn and know, and it's constantly evolving. We're pretty excited to have 2 people from the national labs that support the Department of Energy program. But we'll go through a couple of things here to orient ourselves. I discovered creating QR codes went a little bit crazy, but you can't, these will be posted on our website and they will be in PDF format. So I thought maybe that would be a better way for people to access information. So that's what we're doing. So again, NAMA is the #1 resource for hazardous waste professionals. Started out in 1993. Minnesota had one of the first conferences, had a couple after, and these are amazing events where we have people gather from industry, academia, local government. And again, we focus on supporting mainly the household hazardous waste and VSQG programs and the collection of that waste. That's done by a lot of local government. And we're going to have a conference next year. This is the date. And, you know, what's your role? Do you work for industry? Do you support, household hazardous waste programs or VSQG programs? If it's enforcement, if it's collection, it's all good. And we hope you can join us. So webinars, as I noted, they're available on our website. The first webinar is up, and we also have the presentations available as well. As we work through these webinars, we kind of adjust the titles a little bit because, you know, we talk about what we want to cover and hope to cover, and sometimes it ends up being more. So in the first webinar, we did a lot more coverage of the DOT regulations than I anticipated. And it was a real practical application of those regulations. And I encourage you to check out Chris Blond's presentation where he covers those regulations. So again, we have a series going on here. The times are consistent. We have the different topics. Next up is going to be a focus on electronics recyclers and battery containing device management. Again, I think they want to adjust that topic too. There's going to be a little bit of DOT presence in that one too. So just wanted to note that. Then we have EV batteries, and in February, we'll finish up with extended producer responsibility, although I'm tempted to add another one. I was hoping to cover some of the questions that we had during the last webinar, and there's just not enough time, and they were really good questions. So hopefully we'll put something up on the website that covers those too, since people couldn't see that part of the presentation last time. So I'll just get right into it here. Who regulates? And I think a lot of people know that DOT is a main driver for us. They regulate how we pack our batteries, and most people do the taping ahead of time, get that done as soon as possible, and start storing in that special packaging that's designed for batteries. And again, because Chris did a nice practical discussion of how those regulations apply, I'm basically going to say, check that out. And I have a few, again, I kind of went crazy with the QR codes, but I put up some of the better resources on DOT's website. They have videos, they have great things. And in addition to DOT through FAMSA having requirements, common carriers typically have additional requirements. We aren't doing a lot of mailing through common carriers, but that's just a note. It's another sort of a resource. And our contractors, for me, they've been an invaluable resource. They have figured out the process and the packaging for managing batteries as well as vape devices. And when we see the word disposal here, nobody likes to see that, but that is our option currently for vape devices due to the presence of nicotine in those devices. So that's where those are going at this time for us in Minnesota. So other regulatory bodies include OSHA, and I wanted to make this point in case you don't see it somewhere else. Alkaline, NiCad, nickel metal hydride batteries, they generate a certain amount of hydrogen gas. But lithium batteries generate hydrogen fluoride and phosphorus fluoride, which are horrible things to breathe in. They have a pretty low exposure limit. So if you guys work with your NIOSH guides, go ahead and check that out. This is mainly an issue if one of your swollen batteries punctures. When the batteries are attacked, the exposure is not going to occur. I found a report that I had read earlier on emissions of gases from batteries, and the conclusion was that they can be a larger threat than the heat. And that's why we typically say if a fire's larger than your hand, get your staff out and call 911. The gases are a problem as well. If you want to look at the report, it's right there. The Consumer Product Safety Commission. If you are on their recall lists, you're probably seeing an increasing number of batteries recalled and battery containing devices, bikes. I keep track of those, and they've certainly, you didn't really see them before the middle of 2021. And after that, there's been quite a few. There was I track these, I look at the websites, and I contact the website or the manufacturer of the device if I can, because I want to know what they're telling people to do with these recalled batteries. A lot of the times it's not clear what they should do. Sometimes they say to take them to HHW facilities. And our philosophy in Minnesota is that if they made a product that's defective, they can take it back, especially with the large format batteries that are super expensive to manage. I actually contacted the Consumer Product Safety Commission on one of the last recalls, and I said they don't have information on how people need to ship these back, and that's important because people are this is a situation where if you are an individual shipper and you do this incorrectly, that liability comes back to you. I think what would be really a good help would be if we, as in NAMA or a group of interested people, set up some guidance for the Consumer Product Safety Commission to go through when they have these battery recalls. But it's an interesting area. Let's see
Jennifer?
here. Yes.
There was a question, and I think it was about the exposure issue we're talking about how it compares to lead acid batteries. Do you know?
Oh, well, I do not know. Again, it's a pretty, you have lead, right? And I don't know that that becomes airborne or is a huge issue, but that's beyond my purview, and I didn't look it up. All I focused on was the gases that come out of lithium batteries because they're not good. We can check that out and try and find an answer for you. Apologize, I do not know. Okay. So who else regulates EPA? Would be our other between DOT, I'd say those are our biggest sets of regulations that we have to pay attention to if you're a collector. Which was my request for taking over the webinars, was that he would provide me with a presentation to cover that. I had hoped to get George Kirschner himself on the call or on the webinar today. He's in Austria, and I don't know if it's for oh, my connection says it's unstable. I don't know if it's for business or pleasure. He does a lot of international work, and I just thought, nah, I'll cover it. International Air Transport Association isn't super relevant to our jobs as collectors, but if you ship, if you're a manufacturer and you're shipping, you're probably well aware of those regulations.
Jennifer, can you try turning off your video? Your sound has been going in and out a little bit.
No problem. I will do that. Thank you. Video. Here we go. I hope this helps. Okay, so from Chris's slides, what's the infrastructure laws, battery collection, best practices initiative? Some of you have probably participated in some aspects of that already, but they are working on developing best practices to hopefully increase the number of battery locations. A little more on consumer education. They do have some publications on their website, and reduce hazards from improper disposal. Of course, we always hope that the best practices will be technically and economically feasible. They don't tend to work well if they're not economically feasible. We want them to be safe, obviously, and the one of the goals here, or the thread throughout these infrastructure laws, is the beneficial recovery and of critical minerals. So that is the focus of EPA's effort. And how will they develop that? Well, they'll synthesize input from government NGOs. Maybe some of you participated in this effort. They had a series of meetings with a wide variety of stakeholders, such a wide variety, I wasn't sure they could pull together one report from it, to be honest, but they did. And they also issued a request for information, and some of you probably sent a response in on that. So those are essentially complete. From that, they plan to develop a draft report. They'll provide opportunity for comment, and I hope you all keep an eye out for that and take a read through it and comment. And this report will then be submitted to Congress by November. So I would expect the draft report would be out by July, probably, but we'll keep a lookout for that. The battery labeling initiative, that's a little separate part. Now, this is a voluntary initiative, and I think we all recognize that if we could get an international labeling options that everyone agrees to, which is difficult, I know, that would be ideal, since many of the batteries are not produced here in the US. And I suspect that's why it's a voluntary initiative. EPA can promote it and have discussions and push it, but it's going to take a lot more agreement and maybe some other regulatory agencies to get the labeling changed. This is a new one for me. I had not seen this, and it appears to be to keep them away from children. This is a huge hazard for coin and button cells. Probably the saddest response I ever had to do was we lost a kid here in Minnesota, and I got to do a little write-up for the paper for it. And it was very difficult. This is something you should always mention in your educational materials, is to keep these away from kids. This is also a factor when we talk about how we want batteries to be easily removable. Some should not be. Also, they're going to work more on their communication materials, and that will be helpful as well. I think they're going to emphasize the critical materials recycling, and that's sort of been lacking in some of our educational materials. It's possibly another motivator for people to bring their batteries in. We also have, in our presentation last week, we had the Recycling Partnership present. This is a picture from their site. They do an excellent job of education. They have free materials, and I encourage you to look at their website as well. So mainly for the rest of the EPA presentation, basically we have set up some QR codes so you can take a look at EPA's various documents. If you have no other education material, you can get a good start looking at what they have on site. The best practices and initiative, this is really a placeholder on their website because these are the things that we're all in the middle of working on. Questions, go to EPA. They have great resources here. Kathy Lett and Chris Newman have been invaluable to run questions by. They're great. And even more resources. This is the first report that they did on battery fires. And then this is the result of the stakeholder workshops. So that's available on their site. We're all motivated by these statistics on fires. And that is going to, oh, nope, we got to talk about regulation, don't we? Okay, batteries may be hazardous for one or more characteristics. Could be reactive, could be the level of mercury or cadmium in a battery. So they're regulated different ways. And they all fall under EPA's universal waste umbrella. Technically, household and VSQG batteries are exempt from RCRA regulation. We do it, and I think most states do regulate all batteries that are collected as universal waste. For our collection programs, once we collect waste from the household and VSQG programs, once it's collected, it has to be managed in accordance with RCRA regulations. So we end up needing to understand these very well too, but they're actually relatively simple. It's universal waste. And it's probably, well, it is much more difficult to parse through the DOT and fire code regulations, which we'll get into here. And we'll do that right away. The National Fire Protection Association, I found, has good resources on battery safety for consumers. They have a PDF on the e-bike safety issues, and they also have a safety video related to electric vehicles. And here's a little connection to that. The International Association of Fire Chiefs is geared more toward fire responders. So they are developing a toolkit for responders, fire marshals. They have interesting webinars and videos on the challenges of firefighting related to batteries. This is a link to their site, and they do have a December 7th webinar that is about the specifics related to fighting lithium battery fires. So if you're interested in that, take a look at it. But if you have these fires at your facility, if you don't have something immediate on hand to smother them with, you need to basically evacuate. Here's a picture up in the corner of a battery. This was an e-bike battery that came into a household facility in Minnesota. They came in and dropped it off, put it on the cart. When the person went back to move that into storage, it was so hot, he dropped it on the floor. And so it went into thermal runaway, and they emptied an entire Class D, a large extinguisher on it, and it didn't do a thing because these fires are so hot. And also the individual cells in here, we're doing the Saturn missile thing, popping off into other areas of the facility. So we have to be careful. This is my #1 safety concern for HHW, and I believe we have an average of 10 to 20 calls. We're the bomb squad's best customer, but this is what worries me. We're getting more batteries that are damaged in as well. So that's concerning. I used to do a little bit on the fire code in my presentations, but to be honest, there was really nothing much there isn't in the existing code. But that all changed dramatically with this next update in the fire code. So we'll go through a little bit of that, and anyone who collects is going to have to pay attention to this set of regulations. They're hefty, I would say. So basically the fire code it's a negotiated standard. It's like anything else. Everybody has different interests and you negotiate an outcome. And according to George, he feels pretty good about the outcome we got here with this. So basically there's international adoption, then it moves to countries and state adoption. It can take a couple of years to get through that process, although George mentioned that some are following this already. And the reason I'm going to show some of George's slides is because I cannot find the 2024 code online. I don't know if my Google ability went south on me, but I could not find it. And that is also the reason I needed to borrow. So PRBA, Rechargeable Battery Association, and its members focus on regulatory issues like developing fire code, legislative policy issues at all the way up to the international levels. I think that their website is one of the best resources for links to other areas, and also just with the information available on site. They have a connection to some vape device publications, little short commercials that are terrifying, as they should be. I did not know that all of the battery manufacturers have basically said we don't want our batteries used for vape devices. They were not intended to be used, and those devices don't have the controls built into them that are built into other devices like computers. So as I noted, there weren't really many storage requirements. I think there was a setback requirement for outdoor storage is all there used to be. The new one, they have a whole new section dedicated to it. And this is good. There's a list of exceptions, and that's mainly related to manufacturers of products who've already gotten approval for their packaging, or things embedded in products. So the exemptions or exceptions are not really going to apply to those of us who collect a lot of batteries from the public. There are permits required, safety plans, storage requirements. It's something that we're all going to have to take a look at. If you're building a facility, I encourage you to contact PRBA. George always offers that up. To see if you can get a copy of that code, because I think you need to take a look at it if you're building. So if you have less than about 2 55-gallon drums, and this is really geared toward, and this was one of the negotiated options, it is mainly for business accumulation. They didn't want to have the same level of regulation for people who have smaller quantities of drugs. So batteries. I'm sorry, I was working on a whole bunch of medication stuff before this started. So there's a permit not required, which is nice. Safety plan though. I like seeing this because we have a lot of retail collection, and every time I click it moves. And I am not impressed when I go see it. I looked in IKEA's bins the other day, and sure enough, it's full of swollen batteries, and the lamp collection is full of broken lamps, and it's not good. So containers and requirements are all laid out here for those smaller collection quantities. Must be located not less than 5 feet from exits. That's interesting. You want to be able to get out. Okay, so this is kind of the big deal. You have to secure a permit and have a fire safety plan. Those are easy enough to understand, but the technical opinion and report that you have to prepare, you have to go through that to evaluate the level of hazard. This is still a mystery to me, and I will hopefully find out more about it. I can't tell from what I've read whether this includes battery embedded devices. If you're collecting talking teddy bears and other toys and earbuds, I don't know how those fit into this scheme. If they are considered a battery for the purpose of these regulations, then you're going to be over that 2 drum limit. if it includes electronics and all of that. Construction requirements, of course, so they're requiring a 2-hour rated fire barriers. Horizontal assemblies, this was new to me. I looked them up. It's basically a combination of firewall type of a thing with an insulating layer, with a structural layer, and the finish layer on the outside. And I guess it's basically if you construct a storage area on your own. Then we have also limitations on or exceptions here too. It's limited new batteries. These might not apply. Again, that's not going to be for us collectors.
Jennifer, I'll just note there was a comment in the chat, I assume related to what you're just talking about, that says it has not included electronics with batteries.
Pardon?
There was a comment in the chat saying, or in the Q&A saying it has not included electronics with batteries. I think that's what you were just talking about with the limits.
Oh, thank you for that clarification. I appreciate that. Again, indoor storage is areas that are where you're collecting more than 2 drums. Most collectors have a fire protection system and a fire alarm system. Explosion control. I know that some of the outdoor flam storage buildings have to meet fire code, and there's a variety of ways that they will allow you to do that. I have a snow plow outside my window, which is causing hearing issues, but okay. So again, we have, this is the state of charge is an interesting one. I don't know that there are devices where you can put a bunch of batteries in and get that reduced. So I think that the household programs and recyclers that collect may not be able to take advantage of this. I think it's a great idea if we can eliminate that hazard close to, quickly after they've entered our facilities. This would be great. If you follow that, and I think this is maybe a niche thing for manufacturers or large business generators, but there are far less requirements, but you're going to have to verify your state of charge process. And you'll still need fire sprinkler and detection systems. There are also requirements related to outdoor storage, and there's a few places in Minnesota that have set up basically a flam storage designed for outdoor storage. The cabinets that we use for flam storage, you use them for batteries as well. There's setback distance requirements between buildings and property lines. And we have this reference to either a freestanding assembly or a portable prefab building. Fire detection system is required. And there's a limit on the storage area size. And there's a separation if you have more than one of 10 feet between those. Again, this is just a brief coverage of these regulations, and we're going to need to take a look at that fire code, all of us collectors.
Jennifer, there's a question that I think your last bullet point there answers. Is there a barrier requirement for outdoor storage too? I assume that's maybe meaning that separation.
Yeah, it's a separation requirement. I didn't see that there was a barrier between the storage areas, or if you have 1 or 2 of those prefab kind of flam storage cabinets. I will say that we had, I think I mentioned this last time, we had the county who had the battery fire stores their batteries outside now, and their storage area was broken into, and all of the large format batteries were stolen. And I thought this was related to people harvesting cells, but person also mentioned that They contain lithium, and that's used in meth production. So there is a lot of, well, I'll just say there's more instances of taking batteries from locations that aren't are less visible to regulatory people, I guess. If you have the cell phone towers that have a little building underneath them, typically house a backup battery, and I think all of ours in Minnesota have been broken into, according to DOT. So that is the end of the fire code part. And
Jennifer,
Department of
there's
Energy.
Jennifer,
Oh,
there's
wait.
a question. What is the specific reference to the fire code requirements? Is there a document somewhere?
This is what I was saying, that I could not find it. And
Okay.
I did a lot of different searches. It's got to be out there somewhere. Again, that's why I borrowed George's slides. I like reading code. I don't mind it. I would like to do my own, but I cannot find it yet. I'm going to look though, and we will provide that when we can, because it is, I think, really critical.
Okay, I'll note that. And I'll just also note for you that we're at 1:34 for time.
Does that mean I'm done? Oh, I am done. So I'm just going to introduce quickly Noah and Albert, and they work for the Department of Energy at the national laboratories that support Department of Energy work. And we have Noah from Sandia National Laboratories, and we have Albert from Argonne National Laboratory, and they will cover their different aspects. And I will turn it over to you guys now and quit sharing. Oop. Thank you.
Okay, hope everyone can see my screen.
Yes, we can.
See it.
Okay, great, thank you. Okay, thank you for the introduction. As mentioned, my name's Noah. I'm a scientist at Sandia National Lab. Today, I'm just gonna briefly cover lithium and lithium-ion batteries and some of their safety aspects and how we can go about understanding the safety of these batteries. So let's just jump right in. First, I want to start by talking about the difference between lithium ion and lithium batteries. A lot of times people use the term lithium pretty interchangeably, but you know, words have meaning, and there is a difference between lithium batteries and lithium ion batteries, where in any battery, we will have an anode as our negative electrode and a cathode as our positive electrode, and an electrolyte as a source of ions between that, and a electronically insulating separator between our anode and cathode to stop our battery from shorting. But this separator has to be ionically conductive as well for battery operation. Now, in a lithium ion battery, typically we'll be working with a graphite anode. Graphite is able to charge by intercalating lithium ions into the basal planes of the graphite sheets and then discharge through the deintercalation process. And this is a very reversible process, allowing lithium ion batteries to be charged and discharged repeatedly. During the early stages of this process, I'll just mention that you will have a breakdown of electrolyte onto your anode surface, forming what we call a solid electrolyte interphase. So lithium ion, again, typically graphite anode and rechargeable. When we talk about lithium batteries, we're usually talking about batteries that have lithium metal, and this will be lithium metal on copper, where these are already in the charged state and then can be discharged through oxidizing the lithium to lithium ions, where this can technically be recharged. We can plate this lithium back onto the copper foil. But a major issue with this is the growth of dendrites and ununiform plating of lithium back onto the anode. And the problem with that is this growth can go from the anode to the cathode and cause a short in the system, draining the capacity of the battery, while also posing a risk by generating a lot of heat. So while graphite is rechargeable, lithium metal in lithium batteries is typically primary or single use. So you can't always know whether you have lithium metal or graphite in your battery. Manufacturers won't always say, but if you have a cell, it's always a good idea to look at the spec sheet. And if you want to know if your lithium ion is rechargeable, just look and see if there's anything about charging in the specifications. If there is, that means you're dealing with a rechargeable system. Where lithium metal batteries, typically single use again, will only talk about a discharge and a discharge current. There will be no mention of charging. And so if you don't see a mention of charging, these kinds of cells should never be recharged. Okay, so why do batteries pose a risk? So both lithium and lithium ion batteries have very similar risks, and that has to do with their internal components. So we can look at the combustion reaction here. This is just the general form of any kind of combustion reaction. We see a carbon-hydrogen molecule reacting with oxygen to produce water and CO2. And if we look at the internal components of a typical lithium-ion battery, and lithium batteries will be very similar, you'll see that the electrolyte is comprised of solvent molecules that contain a lot of oxygen, carbon, and hydrogen. And then if we look at the common cathode materials for a lithium ion or lithium battery, we see a lot of metal oxides or oxygen containing species. And when these can decompose, they can form oxygen. So essentially a battery self-contains everything you need to start a fire, as long as there's enough heat or an ignition source, which is quite common when you're dealing with electronics or different kinds of mechanical failures. So, and I think we are all aware of issues of batteries catching fire due to these root causes of having these flammable components, you know, whether it's phone, e-bikes, buses, or planes themselves. But you know, I like to keep a perspective when talking about batteries and battery safety, where anytime there's a battery incident, it will always make the news, but there has never been an accident involving batteries that has been as catastrophic or deadly to people as that has occurred in the oil and gas industry. So it's always good to keep in mind that just because some things are, you know, energy storage is always dangerous, whether it's grandfathered in or a new developing technology, but you just have to have a perspective to the scale of the problem.
Noah, we
So-
had a quick question that I just want to
Yeah.
make sure, because other people might have it too. I know a lot of people are familiar with the term lithium polymer, which is one type of lithium ion. Could you just spend 10 seconds on that from your more expert point of view than me?
Yeah, so a lithium polymer battery is essentially going to be like a lithium ion battery with a different form, or let's see how to correctly go into this. Typically, it means that there is a polymer electrolyte, which can be a somewhat solid state type electrolyte. There are also lithium polymer batteries that actually have the cathode as a polymeric host material for lithium. So it depends on the context. I won't pretend to be an expert in those, but I will say they will suffer the same safety issues as conventional lithium ion batteries. due to the presence of, carbon, hydrogen species, or carbohydrate species, essentially, and an oxidizer. And essentially, yeah, so all these issues will exist in any kind of lithium ion battery. Anytime you have something that stores energy and moves electrons around, you're gonna be generating heat. And if you do that too quickly, it can become a major issue. And many of the internal components of the battery itself do not do well in heat. And so we need to understand why these batteries are failing and their different mechanisms of failing, not only to design safer batteries, but to help regulate different aspects of batteries as well. So what do we actually put into a battery to make them safer? So one thing that exists in a lot of lithium and lithium ion cells is what's known as a shutdown separator. So again, a separator is the electronically insulating portion that separates your cathode and anode, usually just a porous polymer imaged here. And a shutdown separator is a tri-layer polymer, where you can see the cross section here, where the center layer, typically polyethylene, will melt under high heat around 130 C. And when it melts, it will clog the pores of this separator, stopping any ion transport. And this is important because if you stop ion transport, you can stop the flow of current. So in this graph up here, we see charging of a cell in red at a certain current, and the temperature increase here, this trace in purple, where we hit a certain temperature and see at a temperature where our shutdown separator melts, we get the stop of current flow. So this is a way of ensuring that your system won't develop internal shorts through the separator above a certain temperature. Unfortunately, while this works very well at the cell level, it's not perfect. It's been shown for battery packs that have higher voltage tolerances that even after the shutdown of the separator at a high temperature, the actual separator itself can degrade due to the high voltage, reopening ion channels and allowing current to flow even at high temperatures. So a good solution for single cells, but imperfect for battery packs. Another thing that's built into pretty much every cell now that goes into large storage is different gaskets and vents. As I mentioned, there's flammable electrolyte in pretty much every battery. These will vaporize at high temperatures, and we don't want to build up pressure in batteries and have them explode. So pretty much every cell is going to have engineered into it some form of gasket to relieve this pressure. Along with that, a lot of batteries now also have a current interrupt device or a CID. This is essentially a connection between the cathode terminal, the positive terminal, to the actual cathode material through a diaphragm, where if pressure builds up into this cell, this diaphragm will expand and break that connection, disconnecting your cathode active material in the battery to the actual terminal, so that you cannot have the flow of current into or out of your battery. And then also another aspect is the actual design of the cell itself. This is especially true for rechargeable lithium ion batteries, where typically what is done to improve safety is to undersize the cathode capacity compared to the anode capacity in order to have proper performance. What happens if we undersize the anode compared to the cathode is essentially we can fill up the graphite anode with lithium, and then there's still lithium in our battery that will then plate onto the surface of our anode instead of intercalating inside. And that plating again can grow lithium dendrites, which can short the cell. So all of which needs to be avoided for proper use and to avoid catastrophic failure. There's also a lot of devices that go into managing battery packs as well. We have diodes to make sure that current doesn't reverse. These are especially important for primary battery packs so that you don't try, or so that it's not possible to try for reverse current to charge a primary battery. PTC devices, very similar in surge protection. Battery management systems are going to be required for any time you have multiple cells. This is so that you are able to monitor the voltage of individual cells and make sure that you're not either overcharging or undercharging any cell that can lead to failure. External short mitigation, a fancy way of saying designing controls to make sure the positive and negative terminals of a battery don't touch to ensure that there's no short in the system. Ventilation, again, your electrolyte can vaporize, building up pressure in your cell, and you have to make sure if that gets out of your cell through your vent or gasket that doesn't build up in whatever room you're storing your battery. So I talked a lot about, these different protection methods, make sure you don't short your system or make sure you're not generating heat in your system. And so I'm just going to play a short video that demonstrates why that's so important. Okay, so first this is going to show nail penetration. This essentially simulates what happens if you have a puncture in your cell that causes an immediate short. And so you can see in this battery pack here, to devastating effect, what happens a puncture through. Crush is pretty self-explanatory. Thermal ramp is the heating of cells. So you can see there at the beginning, there was a off-gassing event. So that was the actual venting of the vaporized electrolyte out of the cell. And then you can see it starting smoke as it combusts. And that video ends before showing that there's multiple cells in this pack that will all go through a similar process if given enough time. Overcharge. This again is if you charge up a battery, but then there is a mistake in circuitry or improper use, and you keep trying to charge the battery, you can create internal shorts and other chemical effects, which will all lead to catastrophic failure.
No, we have a question about whether the videos will be available, and so maybe we can try to provide a link to that later. And in addition, the recording of this will be available later.
I will try to provide this video, yes. And I might be able to provide better videos of each kind of testing. But yes, I will work on that. And then this last one here is essentially using laser pulses is a indirect way of causing heating and failure. So a lot of things can cause the failures in cells. So it's very important, prevent shorting, prevent heating, and preventing, well, I didn't put overcharge here, but overcharge as well. So the issue, especially when it comes to heating, is a term that's already been discussed today, which is thermal runaway. So I think the best way to start describe thermal runaway is through looking at accelerating rate calorimetry or ARC tests of a battery chemistry. And so what you're looking at in this curve is the actual temperature of the cell and the heating rate per unit time of the cell. And it's important to note when you're looking at this plot, what you're actually seeing is the temperature, this temperature is being generated by the cell itself. Once thermal runaway starts, all temperature is being generated by the cell itself. And that's kind of the proper definition of where the cell is unable to lose heat as fast as it's gaining it. And it does the thermal runaway is actually a series of reactions. So first is the breakdown of the SEI. Again, that's what forms on your anode from the degradation of your electrolyte. That'll happen at lower temperatures. You'll then, at about 130 C, your shutdown separator will close to try and prevent internal shorts. You'll then have cell venting, so your electrolyte will vaporize. And again, this can be an issue if there's an ignition source that can cause a flame to occur. Then in the higher temperature region, you actually have the breakdown of your electrodes. And this is, again, very, you want to avoid getting to this temperature range at all costs, because as soon as you start breaking down your cathode, you start to release oxygen. And oxygen, again, is needed for combustion. So even if you have your batteries in an oxygen-free environment, it can produce its own oxygen. And then you're in a state of catastrophic failure, and there's really no turning back at this point. So you can't stop thermal runaway. Once you're there, it's too late. And the best you can do is, if it's a single cell failure, is trying to come up with ways and put in protections to stop that cell's thermal runaway from impacting other cells. But you can also start to mitigate some danger by choice of chemistry. So we see here that different cathodes release different amount of heat, where we can look at the total heat by looking at the area under these arc curves, where we see that, for example, NMC, which is in most electric vehicles today, will have a total heat release that's quite a bit less than NCA that you'll find in Teslas. You can also find from these tests that the total heat release is very dependent on your pairing of different cathodes with anodes, all of which will affect how much heat and oxygen is released by the thermal runaway. Another thing this was also touched on is that state of charge is very important for total heat release and heating rates, where essentially if a fully charged cell will release more heat than a discharged cell, or even a partially discharged cell. So if possible, always working with a discharged cell will release less heat than a fully charged cell.
Noah, there was a
So,
question about if there's a point, and maybe it has to do with charge or watt hour or anything, where let's see, if a battery goes into thermal runaway, there will be flames instead of only venting. From what you were describing, it sounded like maybe that has to do more with an ignition source, but I wanted to mention that question.
Yes, and that can get, so thermal runaway can be caused, so thermal runaway will happen if you just reach a certain temperature. And venting of electrolyte will also happen if you reach a certain temperature. The flash point of electrolyte is very dependent, I will say. Once you, there's a lot of variables that go into just self-ignition of electrolyte, but yeah, just because you go into thermal runaway doesn't mean you're going to cause a fire. But a lot of times in thermal runaway, you'll also have shorts that are created, which can cause ignition, or if you have some kind of venting or heating that causes a degradation of a battery casing, that can also serve as a point of ignition, kind of like in those videos with the nail penetration or the crushing. There wasn't necessarily an ignition source, but there was enough, or there wasn't an external ignition source. There was something that caused enough of a spark to ignite the electrolyte.
There's a question about, can you speak to LFP and its apparent lack of thermal runaway? I'm not familiar with that acronym.
Yes, so lithium iron phosphate will have a runaway that is not as dramatic as these other chemistries. So lithium iron phosphate, this phosphate's not an oxide. I believe, I don't want to misspeak here, but I believe it doesn't release quite as much oxygen as the other cathode chemistries decomposing. It is also lower voltage, so the total energy stored by a LFP cathode will be less than these other systems. So LFP's lithium ion cells are typically considered one of the safest, but because they aren't as energy dense, they aren't applied in all situations, because people, they want to get the biggest bang for their buck, so to speak. So they will go to a higher voltage chemistry instead of the safest. So for talking about thermal runaway though, and how to prevent thermal runaway, which of course is of great interest, it takes more than just keeping a battery cold. So here we can see 3 examples of a battery. We have our control, just the battery. We have the battery that has insulator between the cells. And then we have the battery with insulator between the cells, and essentially a fuse that between the connections in the terminals. So what happens when we short the center cell in our control is we see it goes into thermal runaway, and that heat will spread to the 2 adjacent cells, heating those as well and causing those to go into thermal runaway. If we just have insulation and cause the same kind of thermal runaway in the center cell, we see that insulation actually doesn't prevent the heating of our 2 adjacent cells, in that these will still go into thermal runaway, because as soon as the center cell is shorted, that essentially, because these terminals are connected, creates a short in these other 2 cells as well. And so here is actually an example of heating of cells without a combustion. But if we have both insulation and fuse protection between terminals, what we see is when that center cell is punctured, it will heat, but that heat will not transfer as greatly to the 2 adjacent cells. So it's not just a matter of keeping cells cold, it's also a matter of dealing with the actual electronic connections to make sure you don't initiate a runaway event. Another option, I'll talk very briefly about these, is just replacing your liquid electrolyte with a solid state electrolyte. These can be oxide, sulfides, or polymers. The other thought is, if not only if you do that will you move this flammable liquid, you can also potentially move to using lithium metal instead of graphite as your anode, which will greatly increase the magnitude of your energy density of your cell. So a recent report that came out of Sandia showed that even if you have one of these solid state batteries that replaces the liquid electrolyte, if you short the system, the heat release essentially will be the same in your battery. But if you have a mechanical failure of your battery or external heating of your battery, then the heat release from the system will be minimalized by moving to an all solid state battery. This study also showed that you can have a solid state electrolyte with just a little bit of liquid electrolyte, quite a bit less liquid than you'd find in a all liquid electrolyte cell, in that under the failure of compromising either the cell casing or external heating, that this solid state electrolyte would then also release less heat. But again, I think the main takeaway would be that, you know, as people move to developing solid state chemistries, shorting through these electrolytes still poses an extreme danger. And I'll briefly talk about this for sake of time, of that if we move to lithium anodes, we can also think about developing new cathode chemistries, moving away from our intercalation host type cathodes to conversion cathodes that will actually react with lithium to form new structures. And we'd want to do that potentially because if these kinds of cathodes are paired with lithium, we can get a much higher energy density out of these kinds of materials than we could conventional cathode materials, where these kind of materials have been demonstrated at the laboratory scale. They're not commercialized yet, but you can imagine as soon as we change the kind of chemistry that goes into batteries, we have to start thinking about how that affects the safety as well. With that, I just like to thank everyone who actually did the experiments I showed today, or I took slides from that made them previously, and all of you for listening. And I'll take any further questions. And if people are thinking about questions, I'll also say I added a lot of backup slides to this talk with resources, more about background into electrochemistry and lithium ion and lithium batteries, if people want to take a look at those. All right, thank you.
It looks like we have some more questions, but it might be good to do the last presentation just to make sure we have time. And Noah, you can see some of them in Q&A and see some of them are pretty specific, but then we can circle back to some of them at the end if we have time.
Okay, yeah, I'll try and address them in the chat.
All right. I guess we are moving on. So my name's Albert Lipson. I'm from Argonne National Lab. So I wanted to I added a slide here right at the beginning of the talk, just now to kind of reiterate what Noah is saying and kind of explain a little bit more about why the different cathode materials do different things. So for the most part, there's really two different types of cathodes. So lithium iron phosphate is a different type of structure than most of the other cathodes that are currently being used. All of these, what we call layered metal oxides, basically have the same behavior, which I can kind of explain a little bit. So what essentially happens is when you pull the lithium out, so this is when you charge the battery, you're pulling lithium out of the cathode structure. That structure actually becomes unstable in these layered metal oxides. So instead of having lithium nickel O2, you have now nickel O2. So this nickel oxide is actually not thermodynamically stable. It doesn't want to be in that structure. It wants to be nickel oxide instead, NiO. So that means it has to lose an oxygen to do that. And as you can see here from some data we took at the APS, so we basically watched the structure and how it's changing through time, basically right around this 250 to 300 degree range, you start to see the structure change over to this nickel oxide phase. And that's when the battery goes into runaway. So this also kind of explains why you want to keep your batteries as low of a state of charge as possible, because you want to keep this cathode material as stable as possible, because this is really what's going to cause the worst kinds of fires and the final thermal runaway. Lithium iron phosphate, on the other hand, so both lithium iron phosphate and iron phosphate are basically stable structures. So there's no reason for it to release oxygen, and that's why it tends not to have very much thermal runaway, but you still have reactions from the electrolytes. So I just kind of wanted to mention that to kind of reiterate that and kind of clarify why people are so concerned about the state of charge of the batteries, because the more you charge it, the more likely it is to blow up, basically. All right, so kind of going into the more recycling side. So I wanted to show this graph. This is an estimate that Argonne did of the expected amount of batteries that'll be available for recycling just from electric vehicles. So the ReCell Center is very focused on electric vehicles. Obviously, consumer electronics are a huge problem as well. I think, you know, the volumes of consumer electronics are somewhere in the neighborhood of 500,000 metric tons. I've never found really good estimates of the amount of batteries that would actually be available for recycling. Obviously, we do a very poor job of collecting the consumer electronics, something we need to work on. So in any case, for the electric vehicles, though, on this side, what you see is starting in roughly 2028 and looking a little bit further, we're starting to have enormous volumes of batteries that will need to be recycled. So this is really the main challenge. And as we're looking forward into the future, the challenge just gets greater and greater. So we really need to solve this challenge soon. So what's currently being done to recycle these batteries? So right now, so batteries are made by mining resources. Then you make basically pure metals or metal salts. These metal salts go into a manufacturing process, as well as some other materials to eventually make the batteries. They go through your car or electronics or whatever. So a lot of people are also looking at what to do with these batteries at the first end of life. So end of life is sometimes classified when the battery still has about 60% of the amount of charge it had when it originally was produced. Sometimes 80%. So you still have actually a lot of capacities in these cells. And the question is, can we use them for something else? So a lot of people are looking at, can we reuse these in grid storage to be able to help balance the grid and store energy from renewables like solar and wind? So there's a lot of work going on there. A lot of the effort is to try to understand how long they would last thereafter, what kind of safety do they actually have, which is actually a primary concern, because if you're using used batteries, how do you know that they haven't been abused in some way? You know, if you have a short that doesn't seem apparent yet, but eventually becomes a thing. So how do you mitigate that? How do you classify batteries? So there's a lot of work going on currently in this second life space. Then obviously at some point, these batteries will end their lives in one way or the other, and then we need to be able to recycle them. There's different places where those recycled materials could go. They could go back into this kind of early stream where you still need to refine everything. You could have sort of an intermediate point, or you could actually ideally maintain the battery materials, and I'll talk a lot more about how to do that. So the ReCell Center, which is the center I belong to, this is a collaboration between a lot of different national labs and universities. The goal of this center is to decrease the cost of recycling. The primary driver for that is really to actually make sure recycling happens so that we get back these critical materials. We don't have these batteries ending up in landfills or just being left on the side of the road and causing environmental disasters. And also it ideally can reduce the energy usage as well as water usage in the manufacturing of lithium-ion batteries. So this center, so this is kind of an older slide, but really what we're trying to do is foster the development of these recycling process, bring together experts across the value chain. So one of the things we do want to do is hook in the people who are actually collecting the batteries, the people who are recycling them, to the final products. If we can help engage those collaborations and discussions between those groups, it'll certainly give us a lot of advantages, and hopefully we can come up with strategies that can actually work in the real world. And then, as I was mentioning, really the outcome of this is we want to keep these batteries out of landfills. We don't want to have to mine as much material. A lot of these materials are mined in other countries, some of which have some issues with how they employ labor and the types of people who are doing the mining. There's a lot of issues globally with the supply chain of batteries. So we want to try to minimize the usage of mined materials. We also don't want to have supply shocks, like if there's global events that happen. For instance, most of the cobalt is actually mined in the Democratic Republic of Congo. If something happens there, war breaks out, a lot of the supply chain could basically collapse overnight, which would be very bad. And then overall, this hopefully will also drive down the cost of batteries. So a lot of good reasons to want to try to recycle batteries. Kind of looking even broader in what the Department of Energy is doing. So the goal of the Department of Energy, particularly the Vehicle Technologies Office, is really to try to reduce the cost of lithium-ion batteries. So one of the things they're trying to do is remove cobalt out of the batteries. This is actually terrible for recyclers right now because a lot of the value in the battery is in the cobalt. There is also a lot of value in the nickel, but if you keep removing cobalt or other valuable minerals out of it, it makes recycling less profitable. So it's kind of this give and take. So the ReCell Center here on the upper right, I just talked about. There was also a battery recycling prize, which I believe there's going to be a second version of, which is meant to try to foster ideas on how to do the collection, storage, and transportation of batteries. So that's something that'll hopefully be picked up again, I believe, in the near future, since the first round is complete. So the ReCell Center, so we do a lot of different things now. So I'm going to talk a lot about direct recycling because that's what we kind of specialize in. We also do other types of recycling and this advanced resource recovery. We're also looking at how do we design batteries that are better to actually recycle. So one of the problems that we see in the industry right now, particularly with the Tesla battery pack, is that they're almost impossible to actually disassemble down to cells. So that you can actually recycle the cells. The Tesla pack uses epoxy to mount all the cells in its pack, and it's very difficult to actually get those cells out. Can you design packs that are easier to actually take apart, easy to get down to the cells, don't have a lot of other contaminants that'll cause problems in your recycling chain, all these kinds of things, as well as we're looking at a lot of these second life usages as well. And then there's a big modeling and analysis focus to try to understand how recycling will affect the whole chain, and also how our processes that we're developing will actually impact the cost of recycling, the environmental impacts, and all those kinds of things. So the slide's really meant to motivate direct recycling, but I'll also use it to discuss a little bit about the other two types of processes. So really, there's three different routes for recycling currently. The first and the largest loop here is the pyrometallurgical recycling. So that basically is when somebody takes a battery, smelts it down to its constituent metals. And so you out of that, you get a metal alloy. That metal alloy then needs to be separated out into its various metals, refined. Then you have to make it into the starting materials for the battery manufacturing process and then remanufacture the battery. So that's one strategy to going about to recycle these. Hydrometallurgical processes mean essentially dissolving the battery in acid. This gets you a solution with all the metal ions in it. Then you have to figure out how to separate out all those metal ions, get back to these raw starting ingredients, remanufacture your cathode material, and then remanufacture the battery. Direct recycling, the idea here is you actually keep those materials as the battery materials. You don't break them apart into their constituent elements. If you can do that, you basically can put those materials directly back into the battery manufacturing process, and you short circuit a lot of these extra steps that occur out here. And the reason why you want to do that really depends on your battery chemistry. So depending on what your battery is made out of, the actual cost of the cathode material versus its constituents becomes very different. So for lithium cobalt oxide, it contains a lot of cobalt, so the constituents are very valuable. So you can actually get a fair amount of revenue back from that. As we reduce the amount of cobalt, the price of the constituents reduces, but not as much the cathode material. And if we move to something like lithium iron phosphate, iron and phosphate are relatively cheap. Essentially, you would get no value if you just broke everything down to the constituent elements. And so if you really want to recycle LFP, you need to be able to do this direct recycling process. There's a lot of good reasons to do direct recycling. The other processes also have a lot of merit, though.
Albert, there was a question about how many locations currently exist that receive and recycle lithium-ion batteries in this manner. I'm not sure which of the processes the person with the question is asking about, but are you going to touch on that later?
I don't have lists of companies in this presentation. I can quickly go over that, at least what I roughly know. There's essentially two primary metallurgical recyclers. They are Glencore and Umicore. And they take shredded battery that's been processed down into what's called black mass, which is basically just taking off all these powdered things that contain the cathode material. So they take those materials, they smelt them, and run that process. There's a lot of hydrometallurgical processors that are now kind of going into production in the US. A few of them are Li-Cycle. It's actually a Canadian company, but they have a lot of facilities in Rochester and New York. Redwood Materials out in California is working on a hydro process. Send Elements, who's building factories in Georgia and I believe Kentucky, is also working on that. Retrieve is one of the places that makes black mass, as well as Li-Cycle makes black mass. So that kind of first steps in this process. Both of them are working on hydro processing now. I don't believe, though, that they've reached commercialization for those. The Glencore and Umicore process are full commercialization at this point. And when I say Retrieve, I always forget what they've changed into, but they changed their name. Any case, oops, skipping forward. So direct recycling. So this is kind of the process for recycling using this direct method. A lot of the other processes are kind of similar in that you first do some sort of reduction step. You either shred the battery or you do what's called hammer milling to break the materials down into smaller sizes. You then have to do something with the electrolyte. People do different things. There's thermal processing. They basically just dry off all the electrolyte. There's people doing some organic or biological decomposition of the electrolyte. For direct recycling, we're basically planning to actually recycle the electrolyte, and I'll talk a little bit about that. Then you have to separate everything. This is very challenging, but there are good methods now that we've developed along with others in the community to actually separate all these materials. You then have to take your cathode material that contains this carbon and binder called PVDF. You then have to get that off, clean that up. And then you actually have to add back some lithium. So I know Noah mentioned the solid electrolyte interface. You lose a lot of the lithium into that stuff basically that forms on the graphite. So you actually have to replace that lithium. And then maybe you have to do some chemistry changing to try to get it up to the current specs of the day. And then that goes back into battery manufacturing. Contamination throughout all these processes is very key. Batteries require very clean materials. You don't want a lot of contaminants in them. They can create shorts and other problems in your batteries.
And someone was just asking to clarify, there isn't commercial scale direct recycling right now, is that correct?
That's correct. The first pilot plants are basically being started now to do direct recycling. Princeton New Energy just built one, and I think some others will be building similar plants here in the near future. But yeah, it's not at commercial scale yet. I've actually gone into this slide a couple of times. So this is what shredding a battery looks like if you do it right. There's a lot of ways to do it wrong, which I think Noah covered very well on what happens to a mechanically destroyed battery. There's a number of reasons why this isn't lighting on fire and bursting into an explosion. So the first thing and most important thing, this battery is actually fully discharged. So this is basically a full-scale car-sized battery. These are 63 amp hour cells. They're quite large, actually. And they are real cells. So first, we discharge them. The second thing is the shredder is inerted with nitrogen, so there's no oxygen. So you don't have to worry about the electrolyte catching on fire just because of a spark being generated during the shredding. We basically have carefully designed everything so that that can be the case. You can see that the battery doesn't even heat up very much. We get up to maybe 34, 35 degrees Celsius, which is roughly 80 or 90 degrees Fahrenheit, barely warm to the touch. If you do this same thing with a charged battery, you will get an explosion. So again, the state of charge really matters when you're handling these batteries. If you have the ability to take them down to a lower state of charge, it's highly recommendable to do so. But preferably not short the battery completely, because that makes a mess from a recycler's point of view, particularly for direct recycling. So as I was mentioning, we do a lot of recovery and reuse of the electrolyte work. We've actually recycled some electrolytes. The recycled electrolyte can perform basically as well as the baselines, or actually typically they cycle a little bit better than the baseline electrolyte that we use. So it can work, and you can actually recycle that. There's questions on the cost benefits of doing so, but it can be done. You can figure out ways of doing all these separations. So we've actually, this is work we've done to separate out the materials. You can get relatively pure fractions of each of the materials by doing these kinds of sorting, and that really can improve these processes compared to just dissolving everything. If you can purify materials up front, a lot of these things are very cheap and very easy to do. In case you were wondering if direct recycled cathodes actually have a chance, so this is some data that I produced from materials we made. You can see that the recycled material is pretty close to the actual commercial material. So this is basically the capacity of the cathode material. So higher it is, the better. And these are just different rates that we're running the cell at. But the performance is very similar. There might be some higher degree of degradation with cycling, and that's something we're kind of working on right now. So what are the other problems with batteries and recycling? So manufacturing scrap is actually a really important problem here. So we want to be able to actually recover that manufacturing scrap. These are basically things, trimmings from the electrodes, cells that were miswound somehow or just don't meet quality assurance. So all of this needs to be recycled, and this is something we're working on at this point. And if you're wondering if this is a real issue, we did some projections of how much scrap you might actually get from the amount of material. And you can actually see that for a while in this kind of near-term region, the scrap actually outweighs the end of life, the EOL material. So scrap is actually going to be a huge impact in recycling. And actually most of the recyclers now have a lot of scrap in their recycling streams. So one other thing I wanted to mention, so we do a lot of cost modeling, as I said, to understand waste streams, the environmental impacts, the energy usage, as well as the cost of all these processes that we're developing. Because we really need to understand what they look like at the real scale so we can adjust our processes to basically be the lowest cost and not have environmental issues. So we do a lot of modeling to do that. And the model is called Everbat. This is actually a freely available model. You can request to have a download of it on our website. And basically what you get out of that, as I said, is the energy usage, the cost numbers, the amount of water usage, all the various emissions that you might expect out of your process. And then you can also have any other waste streams. You also get a breakdown of the cost based on where it's coming from. So materials, labor, capital, et cetera. So you can kind of understand what's the actual main cost driver to the process. Just kind of talk a little bit more about what Argonne has. So we have a big facility for actually doing these things and we're expanding it. So it's just kind of examples of some of the equipment we have. We can run at pretty large scales and we're working to actually scale up a lot of these things. So hopefully you'll get to see that in the future. I wanted to mention also that we do the, at least not during the pandemic, we like to do these industry collaboration meetings. And we have one planned for the end of April. Basically, this is open to the world. Anyone's welcome to attend. And it's a big grouping of people who are interested in recycling batteries. And it's a good way for everybody to talk to each other and kind of understand what's going on. And as I mentioned, this is a big collaboration. Here's the giant list of names of people involved in the ReCell Center and all the various collaborators. So that I'll take any other questions you might have.
Yeah, there's a few more. I'm trying to scroll through to see what we might be able to do easily. I guess this might not be an easy question, but somebody mentioned a lot of this sounds very recent. So what can we do with batteries now? And I think there are some recycling options, but it's something that certainly the government is putting a lot of money into making sure there are more recycling options. Is that correct?
Yeah, so there are a lot of plants basically being built now. There's some established places that can take cells now and recycle batteries. But yeah, there's a huge growth. The government just passed the infrastructure law. As part of that infrastructure law, they put out funding at $50 million per company. These big grants to do battery manufacturing, but that also includes recycling. I know some of the recyclers got that, including ABTC and Send Elements got some of that money. So they're really pushing towards that. There's a lot of work at the research side. Right now, there isn't a huge amount of batteries, but as I was showing in that first slide, it's going to grow dramatically. So really people are kind of scaling up and building up the facilities right now to do this. But there are options right now. And yeah, I mean, there's places to send things.
A quick question, I don't know if you know this, but who makes the typical battery shredders for lithium-ion batteries? Do you know any of the company names?
I mean, I can tell you that our shredder is a Franklin Miller shredder. They do make larger ones. Most people are actually using hammer mills and not these kinds of shear shredders. There's reasons to do that for these other processes. I don't know who most people are going through to do that, but there's a lot of shredding companies around that make things.
There's one person who wants information on that event, so maybe you can connect with them in the Q&A, but one more general question for you is thoughts on remanufacturing.
Yeah.
I think you talked a little bit about some of the Second Life stuff, but if you could touch on that.
Yeah, so the Second Life side is very difficult in a lot of ways. So that would be not really full remanufacturing, but potentially taking everything down to the cell level or just the modules. So a pack is made up of a number of modules, usually something like 6 to 10 modules. It really depends on the design, at least for an electric vehicle. So those modules themselves can be taken out of the pack and then tested individually. You could also theoretically take them down to the cell level. It's very difficult to do that. Most people are talking about using modules. So really the key is the testing side. I know there's work going on the testing side. I'm sorry, I don't have links to all the types of testing people are working on. Currently, there's a lot of industrial folks that have figured out systems to try to do that. There is work now going on as part of ReCell Center to develop some techniques as well that'll be more publicly available, but those aren't available as of yet to determine what's called the state of health. So that's basically how much capacity of the original that you still have left in your battery that you can charge and discharge to. So that's one thing. And then the state of safety, as they call it. So people are looking at that as well. There is some research available, but I think it's still a growing area to really understand. As far as the event, so unfortunately, there's not a website yet that I can share with you. It's still in the planning stages. So once that's available, we'll try to get that out to folks.
Thank you. And I know we're a little over time. There's a couple fire questions. One of them was during Noah's presentation, but it sounded a little bit like something you were just saying. So either of you might be able to take this. Are there research publicly available at the DOE for recyclers to check the SOC? I assume that's like the state of charge or short in the system. And are there any devices that sense smoke unique to lithium ion batteries? I don't know if either one of you know the answer to that.
So if you have it down to a cell, it's very easy to check for state of charge and a short. So a short, if you take a multimeter to it and you read 0 volts, the cell is shorted. If you take a multimeter to the cell and you read a voltage, it should be between roughly 3 volts to 4.3 volts. And depending on the type of cell, you could figure out the state of charge. I don't know if there's tables available for that, but you might be able to actually find that from the manufacturers. It's all dependent on the cell chemistry to go from voltage to the state of charge. What we do for our shredded batteries, we say that anything below 3 volts is considered fully discharged. So we discharge below 3 volts for a single cell. Now, if you have a pack, it's very difficult to measure these things. The packs have various protections on them. They can't just be accessed. You basically need electronic handshakes to have the cell actually do anything. That includes cells like your cell phone. It's very annoying to us. We can't just like measure voltage very easily off of them. Depends on the cell, but it can be difficult.
And then are either of you nor Albert aware of sensors specifically for smoke from lithium ion batteries? Or if you're not, maybe that's something we can follow up with.
There are, I'm sure, HF sensors. Those do exist. I don't think you really need to, though. Basically, if you have a fire in a lithium ion battery storage place, you're going to have the kinds of corrosive fumes that you'd expect. So I would say you don't really need to. I don't know if Noah has a comment.
Yeah, I believe there are that have specific sensors. I just know one brand name like Lithium Ion Tamer, which is a vent system. Because obviously if you have a
We lost Noah's audio.
Oh, sorry about that. It would be helpful if I didn't accidentally hit the mute button. Sorry, yeah, I was just saying that there are companies that do sell sensors. I don't know specifically what they are looking for, but I imagine most do CO2 in so carbon dioxide and carbon monoxide, and elevation of those can indicate venting or combustion of different cell chemistries. And I just want to reiterate one thing Albert said that I also tried to comment on and then realized I was muted when it came to checking the cell voltages. Sometimes lithium batteries can have lower voltages without being shorted. Sometimes it is hard to tell if a cell is shorted or just drained of capacity. That is not always clear. But if you are reading a low voltage or no voltage, it is a sign that your battery is not charged, regardless of if it's just discharged or shorted.
I know we're quite a bit over. There's a couple more. There's another question that gets more into fire details, but a quick portion that hopefully is after, if a battery catches fire after it's put out, is it able to be recycled still?
Yeah, so the hydro and pyro methods would be fine for a battery that caught on fire. Because you're basically recovering the elements are still there. You may lose some things. Certainly you can't recover the electrolyte, but the actual metals should be still there for the most part. And it doesn't create any additional concerns of toxicity.
All right, and then one final question, how prevalent is discharging technology?
So this is, it really depends on the thing you have in your hand. Certainly you can buy battery cyclers. All the national labs have them for cycling individual cells. It can be a little bit tricky though to actually get those to run on real batteries. So it's not trivial to hook up a cell to a discharger for the most part. On the electric vehicle side, I'll say that there's new standards coming about for doing vehicle to grid applications. So that will allow basically a straight hookup from the car onto a grid through an inverter. So that when that technology is available, hopefully most of the car manufacturers are going to go to that standard in a couple of years. So from then on, you'd just be able to plug it in and discharge it. But right now, it's still a concern, and it's not easy to do that.
All right, I think we can call it for questions. Jennifer, did you have any other wrap up you wanted to do?
Nope, I'm good. I'm good.
Okay, well,
Wrap up. I'm sorry. Again, I've got snow blowers around me. We happen to get our first, other people might call it blizzard, but it was only 6 inches, so it wasn't. Thank you all for attending. There were notes on posting things, and we will add some, I'll add some links in my presentation since QR codes aren't great for everyone. I really want to thank Albert and Noah. This is information I haven't heard before, and I really appreciate it. So thank you for being with us, and thank you everybody for sticking with us to the end here, going a little bit overtime. And we look forward to seeing you at the next webinar. And I don't have my slide up, so I can't tell you when it is. It
December
will be
13th, and you can register on the NAMA webpage.
Yes, and we're going to leave the registration open a little longer than we have up to the time of the presentations. So people will be able to register the same day, although we encourage you to do it sooner. Thank you.